All right. Entropy on the molecular scale. These are 4 ways that entropy increases. And on your exam, you'll have a question that says, which of the following will not increase the entropy of a system? And it will give you like 3 of these and then one that's wrong. Yeah, it could. Who knows? All right. But you, like, for sure, Chapter 19 does not have a lot of meat on it. All right. It's not tested very often. There's not a ton of stuff on it, but this is definitely one you need to know. And that is, when does entropy increase? And remember, entropy means disorder. So the number of microstates, and therefore the entropy tends to increase with increasing in, I said 4 things because there was 4 bullets, but there's really just 3, sorry. If we increase the temperature, entropy increases because the particles start to move faster. Entropy is a measurement of chaos, and the faster things move, the more chaotic they are. All right? Then, if we increase the volume of something, now there's more space, so the things will spread out farther, which means they're less ordered or more disordered. All right? Or the number of independently moving molecules increases. Okay? Or, as this says, aka, when stuff dissolves. So if you have NaCl solid, and then you dissolve it and it becomes Na plus Cl minus, or another way to write this is NaCl AQ. Remember, these are the same thing. Now you have 2 things moving about your solution instead of just 1. We have more independent things. If we increase the number of independently moving things, the entropy increases. In my life, one of my least favorite things, and it's funny, I'll leave town for like 2 days and I get home and there's a box of goldfish, like the crackers, because I hate them. There's 2 foods that I ban from my house, and it's goldfish and Fruity Pebbles. Oh, whoa, hey, we don't have to yell. If you think about a Fruity Pebble, it's hard to clean up because it's really small, right? I could pour like 150 marshmallow mateys in a bowl. That might be too much. I don't know, like 70, whatever. But the same amount of Fruity Pebbles is going to be like 1,000. And the likelihood of spilling increases for each microstate, right? Like there's a lot of chaos involved with Fruity Pebbles. I know that's nerdy, but it really is because it's so small and it's easy, it's light, it's easy to spill. Now, a goldfish, I hate them so bad because like my kids, they'll like grab a handful, yeah, and like they'll drop one. And if you pick it up instantly, it's no big deal. It's a fish. But if it even gets disturbed at all, that one fish breaks into 20 million pieces. I'm not exaggerating. And it goes from a lean over and pick it up 1 second job to a job requiring a broom. Or a vacuum. And it becomes a pain. And I don't hate them. I hate my children, I guess. Because they're not picking it up immediately. But it is on. And I don't really hate my children. But it's frustrating because the entropy will increase. Just a tiny bit, like a bump on a goldfish, all of a sudden it's way harder to pick up. And that's because entropy is increased. And once again, Fruity Pebbles, so much more of them per bowl. So much more chaos. So much more opportunity for a mess. Yeah, and tomorrow. All right. Another way that entropy increases is by changing the state. So a gas has more entropy than a liquid, and a liquid has more entropy than a solid. And if you just think about it, it's kind of obvious. Gases, the particles move faster, they're more spread out, they collide more often. All of that is increasing the amount of disorder or chaos. Yep, we're going to get that math coming up. Don't worry, we never have to calculate like the entropy of something because that is extremely complicated and way beyond the math that we have to do here. But we have to find the change in entropy, which we've been doing forever. Like you have an initial, you have a final. Like you do it all. All right, good. All right, solutions, and we sort of already said that. When a solid is dissolved in a solvent, entropy increases. It says generally because there's a very small, once in a while, where the temperature of dissolving drops so hard, or so far that it overcomes the separation. But really, just stick with it. When something dissolves, entropy increases.
Drop something into water and when it dissolves, it takes it.
Yes, there are things that can do that. They're pretty rare. There's a cool, I don't have this stuff because it's expensive. But you take a wood block and you soak it, so it's kind of wet, like overnight. And then you put a beaker right here on the block, and no one really knows it's wet when you do this demo. And then you put this stuff in to dissolve, and then you pick it up to show the kids, and it's stuck in the block. Because it froze to it. It froze that little layer right there. Well, it's different than that, but it's sort of the same idea. It's a surprise. How about that? All right. So in general, this is just the same ideas. Entropy increases when gases are formed from liquids and solids. Liquids or solutions are formed from solids. The number of gas molecules increases, or the number of moles increases. Okay, so they could also, so if you have H2 plus O2, it goes to H2O, and you balance this with a 2 and a 1. And they're all gases. Okay, and let's say the temperature remains constant. They'll say which side has more entropy, the reactants or the products. And there's just one easy way. This one here, the number of moles increase. All right? And the number of gas molecules also increases on this. So this, you would say, has more entropy. This has less. Okay? Now, we know that entropy increases. So if you remember a second ago I said the temperature maintains the same. It doesn't really. So we would actually have heat here, which would overcome and cause this to overall increase entropy. But just the idea here of the number of moles increasing. Okay? We good with that slide? I see some copy. It is. Never mind. This is the third law of thermodynamics. You don't really need to know much about it. But by the way, here it is. Change the pen, please. The entropy of a pure crystalline substance at absolute zero is 0. That's the third law. If we get something to absolute zero, it has no entropy at all. Because there is no vibration. There is no movement like traveling from here to there. They are locked in and everything is holding perfectly still. Okay? If we increase the temperature, it does start to vibrate and things happen. What's that? I would imagine it'd be super easy. I don't know that they've ever tested how. No, they got them super close. But yeah, typically the colder you get it, the much more brittle things become. On Earth, they have never gotten to absolute zero that they've observed. Because to observe it, we need tools that measure how fast things are moving. And those tools themselves destroy absolute zero just by measuring it. It's kind of weird. But it does. It's like what's that? Yeah. The tool itself only works if it has parts that can move. So you take something where you think nothing's moving at all, but your tool has to have movement. It ruins it. So when they say we haven't achieved it, we haven't proven if we've achieved it yet or not. Now, we know absolute zero exists in space. It's pretty easy. And that's because there's no matter. If you have just a meter of space stuff and there's nothing in it, then that's pretty easy. It's at absolute zero. What's that? The average temperature. There's plenty of absolute nothingness in space. Radiation can travel through here, but if there's nothing for it to hit, it will not give its energy to it. So it's pretty tricky, but pretty cool at the same time. Okay, next up, standard entropies. All right, ready for some math? Don't do that. It's subtraction. Don't panic yet. Okay. These things right here are molar entropy values of substances in their standard states. All right. So this is a new thing to us. It's going to be S naught. All right. That means the molar entropy values of substance in their standard states. The naught always means that standard conditions. Okay. Now, I often just call this snot because it's sort of funny and it's S naught. Snot. I don't know about your attitude today. Anyway, these are snot values for various things. Okay. Now, if you have these kind of math problems, you'll always have these numbers in tables. Okay. Standard entropies tend to increase with increasing molar mass. That is something you should put in your notes. Usually the heavier the substance is, all right, the more entropy it will have. Yep. More protons, more neutrons, more electrons. Yeah, uranium would be very high. All right. Larger and more complex molecules have greater entropies as well. So, it's probably never going to ask you, but if you had like a cyclohexane versus a hexane, this one is longer and more complex. This one is more ordered. So this would have more entropy than the cyclical version of the same thing. All right. Now, this looks tricky, but we've done this exact math in other chapters, so don't have a count. Entropy changes for a reaction can be estimated in a manner analogous to that by which delta H was estimated. So, delta S naught, or the change in standard enthalpies, is equal to the sum of the coefficients of the S naught products minus the sum coefficients delta S naught reactants. So we have, I promise, we've done this before. You didn't love it because it's not hard, but it takes just a lot of work. It's being a good accountant. Yeah, same thing. Bond enthalpies. So we tie it to these tables. And like the table will be a lot bigger, but then you're literally just plugging in values. It's just like chapter 5. You just got to be careful. Okay, now we're going to introduce a lot more of this, but then we'll do some problems when we get back. Does that sound okay? So, entropy changes in the surroundings. So heat that flows into or out of the system changes the entropy of the surroundings. For isothermal, do you know what iso means? Same. Thermal temperature. All right? For an isothermal process, delta S of the surroundings now is equal to negative Q of the system over T. Remember that Q is heat. Okay? So we learned this in chapter 5. At constant pressure, Q system is simply delta H for the system. Okay. Now, I would not, my friend, I would not write all of this stuff because we're going to use this to come up with an overall thing. And if you had AP Bio, it's finally like, oh, hey, this is one thing we learned in AP Bio that applies to AP Chem. Okay? The universe is composed of the system and the surroundings. Therefore, the away line. Delta S universe equals delta S system plus delta S surroundings. For a spontaneous process, delta S universe is always greater than 0. Okay, on this slide, this is all that, and you should probably have that. Well, I don't know if you wrote it exactly that way, but there was a sentence like in the middle of yesterday that basically said the same thing. So if it's spontaneous, entropy is always increasing or always positive. Okay. Now, you don't need to write all that stuff. And don't write most of it. Well, hold on, you might need that. Let me see if it summarizes it coming up here. Okay, there we go. So this becomes this equation. All right, multiplying both sides by negative t ends up with this. So negative t delta S of the universe equals delta H of the system minus t delta S of the system. Complicated, but we'll be fine. All right, negative t delta S of the universe is defined as Gibbs free energy, or delta G. We're getting to what matters here in a second. All right. When delta S is positive, delta G is negative. Therefore, when delta G is negative, a process is spontaneous. This must be something that you know. We are going to calculate delta G, but you have to know what it means. If you get a negative value, it means the process is going to happen without any outside intervention. So if you get a positive, then it means it won't, or that it's non-spontaneous. Okay, and it comes from all this math, but we don't necessarily need to do the math. This is complicated. All right, this looks ugly, but we're going to be all right here. Oh, that piece. No, still. There we go. All right, if delta G is negative, the forward reaction is spontaneous. If delta G is 0, the system is at equilibrium. If delta G is positive, the reaction is spontaneous in the reverse direction. Okay, you already wrote one of these, but all of them are absolutely important. Because for the AP test, if you get stuff from chapter 19, it's almost always just in the multiple choice. And it almost always has to do with these qualitative ideas about spontaneousness. All right? There is a chance you would get a Gibbs free energy math problem, and they're not bad. So if you get one, don't panic. Okay, same math as S. You will be given these numbers from a table, and you just plug them in. When you plug them in, you'll get an answer that is either positive, negative, or 0. And based on what you just wrote, you should know and be able to tell us, will it go forward, will it go reverse, or is it at equilibrium, meaning it goes both ways at the same rate. Okay, so first math and then chemistry, which is backwards of last chapter, because that was first chemistry, then math. You okay with that? All right, now there's a different way to calculate Gibbs free energy, but it's not that bad, and that's this. So, at temperatures other than 25, which is more common, you have delta G, and this one is absolutely imperative. Now, this is given to you on the AP test, so you don't have to memorize it, but you definitely have to know how to use it. So delta G equals delta H naught. You can find these in a table, or it's given to you in the problem. Minus T delta S. And then there's this question. Have a short discussion. T is temperature here. How does delta G change with temperature? Have that short discussion. So that's good. All right. So as temperature changes, this term becomes more negative. If S is positive, it's tricky. Okay? This term is what's going to be real tricky here. You are subtracting a number that may or may not be getting bigger based on the entropy. Okay? So you got to be real careful. But just to answer this becomes increasingly negative. All right? Now, you need to, let's see what this is. So there are two parts of the free energy equation. Delta H, which is just the enthalpy term. And that's usually pretty easy. It will just tell you that in a problem. That yada, 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 and 98 kilojoules were released or absorbed. And there's your 98. And then there's this T, temperature, times your change in entropy. So the temperature dependence of free energy then comes from the entropy term. Because remember, you're going to subtract T delta S. If this is a negative, then you're really adding. Right? If this is a positive, then you're really subtracting. So you have to be extremely attentive to detail. So you are really good at that in this class. Okay, here is a table, and even I had this table back in the day, and I really struggled with it. I'm not going to lie. Chapter 19 kicked my butt for years. Like, it's tricky. So while I talked to Rasmussen, Rasmussen's going to bask in my glory while we talk about this. So that would be nice. Oh, ouch. That was savage. You feeling okay? Yeah.
Yeah, I'm in a Friday state of mind.
Yeah, so am I. I'm in a Friday. Yeah, I don't know why I paused that. Just out of sheer habit. Okay, here we go. This is a table that would be really nice to memorize. If delta H is negative and delta S is positive, then negative delta T, delta S is negative, delta G is negative, and it's spontaneous at all temperatures. It's up to you. It's in your book. He's taken a picture of it. But the more you know this table, the easier the problems will be. Now, I know it's a tricky table. There's no lying about it. Like I said, I struggle with chapter 19 all of my personal science career. If you have a positive and a negative, then you end up with a positive and a positive, and it's non-spontaneous at all temperatures. Okay. These down here are not as hard, but they're not as useful either. Negative, negative means this is a positive, and delta G could be positive or negative. And it means it's spontaneous at low temperatures, but non-spontaneous at high temperatures. Positive, positive means this is a negative. Your answer could be plus or minus. That's spontaneous at high this time and non-spontaneous at low. So, you have a test question where I'm going to ask you what delta G naught is at like 25 degrees. And then I'm going to ask you what delta G is at 500 degrees. And it's going to, the spontaneity is going to change based on this stuff right here. Okay? It's going to say, is this spontaneous? And one is going to be yes, and one is going to be no, if I remember right. Oh, that's embarrassing. Just kidding. It's only embarrassing in church. And the old lady cannot figure out how to turn her ringer off for the Wi-Fi.
That happened in the temple.
Oh, that's awful. Yeah, that'd be my mom someday. Okay. One last math thing. Oh, fine. Just kidding.
I didn't say it good. No one wants it.
Still. Under any condition, standard or non-standard, the free energy change can also be found in this way. So under standard conditions, all concentrations are 1 molar, so Q equals 1 and LNQ equals 0. The last term just drops out. All right? But under non-standard, okay, so kind of ignore this for a second. So non-standard conditions, meaning different molarity, essentially different temperature, whatever. We now have this. Delta G equals delta G naught. That is found in a table. All right, plus RT ln Q. Remember, Q is the equilibrium expression. That you may not be at equilibrium, though, right? And then T is your temp in Kelvin. And then R is your gas constant. But it's not 0.0821 because it's a different unit. So I call this 8 pi is how I memorized it when I was a kid. 8.314. So when we do energies, and I know it's weird, it's like 0.0821 is not 8.314. But if you change the units, we have to have different units to get it to work with these entropies. Entropies, sorry, is where this comes in. We end up with a different thing. Well, no one on the internet would have cared about Jenna Mortensen wearing my Apple Watch like I win a stupid competition. Oh, no. Okay. So here's some stuff. At equilibrium, Q equals K and G naught equals 0. The equation becomes this. Rearranging this becomes this. Or, here's another way to find K. How cool is that? I will tell you something.
What do we use?
If I put it in a box, you definitely should use it.
What are we going to use?
You could use these. If you have K, you can find G. If you have G, you can find K. Then I drew a cute little red flag because people screw this one up an unbelievable amount because you don't type your exponent in correctly. That sounded poor.
You don't type your exponent in
Correctly.
Oh.
You must absolutely put this in parentheses. The negative, it doesn't really matter, I guess, but it's the negative of this whole thing. But I guess if it's inside, it doesn't matter, right? But you have to have the whole exponent there. Or what you do is you take E and you're raising it to negative delta G, and then you're dividing that answer by RT. And that's an extremely different mathematical process than what this is asking you to do. Isaac doesn't believe me, so he's going to prove it
my
wrong.
calculator doesn't block the exponent.
Okay, well maybe yours is fine then. Oh hey, we're done. Give me some values. I don't know. Delta G, let's say it equals 10. R is 8 pi. And T. G naught means that. Room temperature, room pressure, 1 molar concentrations. It means I just do a nice equation. I do a demonstration on my desk. That's essentially what that means. Yeah, you can find those values in a table. Okay, well, FYI, everyone, Isaac's calculator is amazing.
It's actually super annoying. All those, like, negative
Until today.